It's time to quieten down because we have lots of interesting things to talk about today. We're going to talk about earthquakes, and this should be something that is important for every single person in this room because we live in South California, and in South California there are large earthquakes, and we are way overdue one, and you need to know what sort of magnitude earthquake could happen and why it's going to be here. So as a quick reminder, quiz 2 is going to be available from 2 p.m. today until 1 p.m. on Monday, just like last week. Again, there'll be 10 questions, 2 points each. A couple of them are easy, a couple of them definitely aren't, and you should see it as a challenge. Today is also the last day to drop. So if you're fed up of my voice already, now would be the time to drop the class. And also changing the grade option. You can do it by requesting permission in the next couple of weeks, but if you already are feeling uncertain, then now would be the time to think about that. And then two other things. Firstly, I have an all-day meeting on Monday, so I'll definitely be coming to lecture, but I won't be able to hold office hours after class, unfortunately. So I'm sorry about that. But I will be around as usual on Tuesday, Wednesday, Thursday if you have questions for me. And then the very last announcement is that, unfortunately, we're not going to get the YouTube video up today. We've just run out of hours in the day that is possible to do that. But what I am doing is I'm recording this on what's called UCI Replay. And what you'll get is my voice and what's on the screen. So you won't get my demonstrations or me prancing about in the front, but you'll still get the content. And I'll send a link out to that later today. And if you have trouble accessing it over the weekend, then I will be on email. Okay, any questions about any of that? No? Okay. So we just need to finish off our last little section of Wednesday's lecture, because on Wednesday we spend a lot of time talking about plate boundaries. And in particular, how the different plate boundaries have different processes occurring at them, and those different processes result in different types of landscape features, different types of volcanic activity, different types of earthquake activity. And it's really cool because finally we have this unifying sort of theory that can explain why we have the Andes mountain range next to a big trench, why we have the Aleutian Island arc in between Alaska and Russia next to this gigantic trench. We can start really explaining some of the patterns that we see, things like why we have a mid-ocean ridge in the middle of all our ocean basins. But we missed one last one. We ran out of time, and so we didn't quite get to continental-continental convergence. But this is a pretty simple one, so we'll go through it quickly. So this is what we looked at last week. We looked at transform boundaries, and what's our nice, easy example of a transform boundary? San Andreas, and that's what we're going to talk about today, movement on the San Andreas. Then we have divergent boundaries, and that can occur within continents to create new ocean basins, like what's happening in the Rift Valley in Africa today, in the Basin and Range area near us in the Colorado Plateau. And then we have those divergent, those mature divergent boundaries actually in ocean basins where they're creating new ocean crust as they spread apart. And then we had our convergent, and we had 3 types. We have where ocean and ocean come together, and you remember I said I didn't like that diagram because actually where that crust is subducting down, where that plate is sliding back into the mantle, we have sort of melt happening, and that creates these volcanic island chains that run sort of parallel to our nice trench. And then we have convergent boundaries where continent and ocean plates are coming together. And in those, the ocean plate again sinks down underneath and sinks back into the mantle. And again, where that happens, there's melt, and that melt rises and forms these sort of volcanic chains along the edge of the continent, which is what our Andes were. And then lastly, the one we didn't get to was where we have continent and continent coming together. And do you remember we were saying that the continents have actually been increasing in area through time because we can't subduct continental crust. It's too light. It won't sink back down. And so what that means is that when we get convergent boundaries, where we get continents and continents smashing into each other, they don't sink. They instead sort of mash together, and we start building mountain ranges. And just like, you know, with an iceberg where you have a certain amount above water and quite a lot underneath, it's exactly the same for continental crust. In order to balance out all of that extra mass that we have in our mountain range above sort of the sea level, we also have quite a large thickness of continental crust, of continental plate underneath that as well. And so here is our example where we have this collision zone and our big mountain range forming. So, obvious question of the day, where is this happening today? Himalayas, thank you. Someone's sort of on the ball. Okay, in the Himalayas, this is the only place where we're getting active convergent boundaries today, and it's creating our huge mountain range, that's a really tall mountain range, including Mount Everest, the highest point on Earth, and those are continuing to grow. If you climbed Mount Everest 10 years ago, then you climb slightly less high than someone climbing it this year or next year, because they're still converging, they're still growing. Okay? So that's our example of continental convergence. Okay. But I have a question for you, and it's probably an obvious answer because I'm asking it, which is, do those plate boundaries explain all of the volcanic activity we see and all of the earthquake activity? So here's this really beautiful map again, showing the earthquakes that have happened through time. Can anyone see a really obvious point which is not on a plate boundary where we get earthquake activity and volcanic activity? Yes. Hawaii, absolutely. Look at Hawaii there. Beautiful green dot in the middle of the Pacific plate. It's not on a plate boundary, but who's been to Hawaii? Probably quite a lot of people. Yes. I'm so jealous. I really want to go. But yeah, if you go there, you can see the volcanic activity. You can see the lava fields. If you're lucky enough to go when it's active, you might see sort of moving lava. And there's also earthquake activity associated with that. So, how on earth do we explain this, given what we've just talked about in terms of plate tectonics explaining volcanic activity and earthquakes? So there's our earthquakes. There you can see our volcanoes in the middle of that Pacific plate. But it is worth noticing that, look, we also do have other places, perhaps say the southern part of Australia there, where we also have volcanic activity that we can't easily explain using our nice idea of plate boundaries. And so what we're going to talk about is hotspots. So this is the reason that we have those beautiful Hawaiian islands in the middle of the Pacific plate where they otherwise shouldn't be. And the idea behind hotspots is that, for some reason that we don't have that good an idea about, an area just on the outer core mantle boundary, so right down deep, gets a little bit warmer, and that rises because it's less dense. Remember, warm stuff is less dense and will rise, just like your hot air balloon will rise. And that mantle material rises up as a plume, and it rises up until it hits the bottom of our plates, and then it might spread out a little bit. Okay? And these are usually really very long-lived. Okay? And they also, we can assume for the purposes of this class, are stationary. And that's nice because when we talk about plate movements, everything's moving relative to each other, and the pole is also moving around, and so it's very difficult to find one single reference point that is always in the same place. And that's why these hotspots are great, because they mark one spot on Earth that isn't moving. Okay? But of course, what's happening over the top is that the plates are moving. So here are some of the proposed hotspots. Some of them are definitely ones, things like under Iceland, happens to be at the same point as a divergent boundary, but the reason that Iceland is there is that we've got that extra bit of heat, extra bit of melt happening, which has generated an island rather than that ocean ridge. Things like the Galapagos Islands are associated with a hotspot. And then, of course, we've got Hawaii, Yellowstone, also a hotspot. So anywhere where we've got this activity off plate boundaries is what we think is happening is that there's hotspot activity there. So let's look more carefully at Hawaii. And not only at Hawaii, but as you know, there's a chain of islands. And not only is there a chain of islands, but if you follow along that same line, then underwater, they may not break the surface of the ocean anymore, but if you follow along, there's also a series of undersea mountains that were probably once islands and have worn away. And we call these the Hawaiian Islands and the Emperor Seamount chains. And the seamount is just an underwater sort of mountain. Okay? So my question for you is, thinking logically about this, if my hotspot is staying in the same place, which of the Hawaiian Islands or Emperor Seamounts, those underwater mountains, formed first, as in is the oldest? Which of those is the oldest? So pick the letter that you think represents the oldest. A few more seconds for the people to vote. Okay, so let's take a look and see what people decided. So there's a little bit of dissent again. Okay, so which is the newest island? Which is the nice active island forming now? Hawaii, okay? It's the newest one. It's the one that actively has volcanic activity and is forming now. Okay? So, if we think about this, we're going to be moving backwards in time, right? Okay? So the people that put A would be correct. Yes. Okay. So let's take a look at why that is. So I have a little video here that makes it perhaps a little bit easier to think about. So let's take a look at this video. So I'm going to skip forward because it's a bit slow for a while. Okay. So here's our heat rising. That mantle plume is hitting the surface, and some of that melt comes up through the crust and produces a nice little volcanic island. And that's where Hawaii and the other island chains have come from. But remember, our mantle plume is staying in the same place, but what's happening to the Pacific plate? It's moving, okay? So over time, that Pacific plate moves along, and what we get is that heat plume staying in the same place, and so it produces another island. And then further along, it'll produce another island. Okay? So if we therefore look back at our map, you can see that this is where the hotspot is today. This is our island that's forming today. But as the plate has moved, you can see that we also have a chain of islands running along here. What do you think happened here? The Pacific plate decided to shift in another direction, so that the direction of the plate movement changed at point B, but we still have our chain of now seamounts running up here, and actually A was the first one, so you can reverse the plate movement, and A would have been here, and then the plate has slid along and produced these islands behind it. Okay? So have a think about that. Draw yourself a couple of diagrams if it makes no sense still. Okay. Because I now want to talk about earthquakes and us. Here is the beautiful San Andreas Fault, our lovely transform boundary that separates us on the Pacific plate from more or less everyone else on the North American plate in the US. Okay? And here you can see the date of the last big earthquake in different sections of the San Andreas. What do those numbers suggest to you? We're in a little bit of trouble, yes. So remember, we have that big earthquake in San Francisco in 1906. That's when the northern section of the San Andreas last went. The middle section, we can look back at the historical records, and that section last went in maybe 1857. But our section, from maybe the Salton Sea up sort of past Los Angeles, hasn't broken since 1680. So, of all of the sections of the San Andreas, we're really where the most stress is stored up and where it's most likely that there will be a significant earthquake in the future. Okay? So, and then there's a little section in the middle that just creeps. It doesn't actually break with earthquakes, it just slides past itself. So what does that mean? That means that the southern section of the San Andreas Fault will break. When it does, there will be an earthquake. This isn't a maybe. There will be an earthquake. And the details of how damaging that earthquake will be, how dangerous it is, will depend on a number of things. First of all, how large it is. The problem is, given it's been so long since it's broken, it's stored up a little bit of extra energy. The pattern of shaking and damage, so exactly how the rupture happens. Things like the time of day. Are we all safely in bed? Are we traveling somewhere? What will happen there? Weather conditions. Why do you think weather conditions might affect how much damage there would be? Fires, maybe. Fires are definitely a really threatening part of earthquakes in LA, because at the same time all the gas mains break, things like the water pipes will break, and so how do firefighters get hold of water to fight the fires? But thinking back to Wednesday, was anyone trying to travel along the 5? Yeah.
I mean, if there's increased rain activity, it's going to make traveling a lot more difficult in general, and you have to take into account we do live in an area that's very prone to landslides as well, so saturated soil is more likely to break things.
Absolutely, you've absolutely got it, which is that if it's been really rainy, like on Wednesday, we saw that the 5 was closed for a while because of a big mudslide and landslide. Really waterlogged soil will be much more susceptible to things like that. So if we'd had a big earthquake on Wednesday, we'd have seen many more landslides than perhaps if it's been dry for a long time. Numbers and sizes of aftershocks. So we just don't have one earthquake. Usually there's a sort of little aftershocks, little subsequent earthquakes, nowhere near as big as the first. But they can be substantial, so that would also have an effect. And here's a number that should make you think. If we look back and we date different layers of sediment and look how often there seems to be an earthquake on our section of the San Andreas, on average, it tends to break and have an earthquake every 150 years. It has now been over 300 years since we last had an earthquake, okay? So this is something that we really should be concerned about. Okay, so what is an earthquake? It's something that we sort of intrinsically know, but let's think about what it is. So we have what we call the elastic rebound theory, which basically explains what's happening. So for example, if we built a wall across the San Andreas Fault, remember that those plates are moving past each other, so each year there's a little bit of movement. And what happens is that those rocks can store a certain amount. They don't slide straight away because there's a lot of friction between the rocks. And so what happens is that they store that elastic energy and they bend a little bit, and you can see our wall bending a little bit. And then at some point, enough energy is stored that it overcomes that frictional force, that force trying to prevent it move, and it will slide. And it won't slide and keep going forever. It'll slide a little bit. And then the process starts again. And that release of that elastic energy is what we see as earthquakes. And I'm not doing magic. This isn't helping my Harry Potter comments in my evaluations. But I have my little stick here, and I'm going to demonstrate our elastic rebound theory, which is that if I put force on this, you can see it will bend a little bit. Oh, and break. Okay, so it didn't bend very far. It couldn't store a lot of elastic energy. But when it broke, it formed back into the same shape it was before. It bent, but when that elastic energy was released, it vibrated, and that's our earthquake, that's our seismic waves traveling out. And then it formed the same shape it was before, which is a nice straight wall, but now it's offset from each other. Okay? So that's our little earthquake, and that's that energy, that elastic energy being released, which is what we see as an earthquake. And all of those diagrams you see in those books are really sort of designed because of this lovely little image that was taken after the 1906 earthquake near San Francisco, and some guy did, in fact, build a fence across the San Andreas Fault. And you can see that there's a nice big sort of 2.6 meter or so offset. And it's not just things like fences that we build that do that, but things like rivers, mountains, and things like that will get offset by these sorts of events. Okay, so here's a couple of terms for you. Most people have heard of the word epicenter. That's what the news shows you when there's an earthquake. They say the epicenter was here. The epicenter is actually the point on Earth's surface immediately above where the earthquake happened. So earthquakes will usually happen on a fault. A fault is a break in Earth's surface along which movement happens. Okay, so we have our San Andreas fault, and I'll show you some more in a second. And then our earthquake actually happens probably at some depth on that fault. Not exactly at the surface, but at some depth. And the exact point where the earthquake starts, where the seismic energy travels out from, is called the focus. So that's the point where the earthquake actually occurs. The epicenter is is the point immediately above that on Earth's surface, and that's what we draw on our maps. But we have the San Andreas fault. Do we have any other faults running past us that we should be concerned about? Yes. We have a lot of faults running past us that we should be concerned about. Have you ever heard of the Newport-Inglewood fault? It runs through Newport Beach. It's pretty close. We also have things like the Elsinore fault, which runs the other side of campus. And you can see that the color coding there represents the magnitude of earthquake that we can sort of estimate has happened on these fault lines. And you can see that the Newport-Inglewood, the Elsinore, the San Jacinto, they've all had earthquakes on them, approximately 7.5 to 8. That's substantial. That's not messing around, okay? And so we also need to be aware of those. It's not just the San Andreas that goes. It goes more frequently, perhaps, than these others. But we don't have a great sense of how frequently these other ones break. We haven't had a long enough history to know that. And then you can see that there's a whole bunch of other things as well. The point is that there's not one nice fault which the plates sort of slide past each other. Actually, that movement is accommodated on a number of different faults. And it's not just the San Andreas that we need to think about necessarily. Okay, so seismic waves, this is what you feel. Who has felt a large earthquake? By large, I mean more than a 5. A few? Are you all too young for Northridge now? Were you born in 1994? Only just, and most of you, oh my goodness, you're so young. Okay, so that was the last big earthquake in the LA area, and it did a lot of damage, and it killed people, unfortunately. And really what sort of is damaging is this energy that is being released and sent out in the form of seismic waves. That's what causes the shaking that we experience. And for those of you that have felt large earthquakes, and even smaller ones locally, you get a little rumbling first, right? You get a little bit of a rumbling, and then perhaps it gets a little bit more significant. And then usually after that, there's another big jolt. Everything doesn't arrive in one go. You can actually feel this. And next time there's an earthquake, I want you to think, apart from, let's get under a table, see if you can identify those different arrival times of the different waves. Okay. So we have 2 families of seismic waves. We have things called body waves, which will travel outwards in all directions, so they will go through the Earth. We also have surface waves, and they will only go along the surface, which is nice and easy to remember. Okay, and these can be recorded by seismometers, and you can imagine how as you get shaking in the vertical direction, that moves the spring up and down, and so that leaves a mark on that sort of rotating roll of paper. And then the same idea with the pendulum is that as the ground moves under that pendulum, the pendulum stays in the same place, and so we'll draw sort of horizontal lines marking the horizontal motion. And so we get something that looks a bit like this. We get what we call the P waves arriving first, then we have S waves, and those are 2 types of body waves. Those are the ones that travel outwards in all directions, including through the Earth. Then we have our surface waves. And our surface waves, you can see from the size of them, are usually the more damaging part of the earthquake. Those little rumblings you feel first are the P waves and the S waves, and then the real jolt is from those surface waves. So let's look at P waves and S waves. And I need a volunteer who signed our video waiver form. Do I have a volunteer? It's nothing too onerous, I promise. No? No volunteers? Come along, come to the front. Excellent. One brave soul. It's not too challenging, I promise. Okay. All I want you to do, yes, round of applause. Okay, just hold that there, and hold it on the ground. Okay, so I'm going to demonstrate to you the difference between P waves and S waves. So P waves are compressional waves. We're so compressing something, and so P waves travel like that. Okay? They compress in the direction that they're moving. If we talk about S waves, I like to think of these as shear waves, or you can think of them as shape waves. This is what happens in shear waves. Okay? So P waves travel the same direction, S waves travel side to side. Okay? And this is why P waves will travel straight through the Earth, even through liquid. S waves won't. Okay? Thank you very much. That's all. Great. Thanks. So P waves are these compression waves, and they travel just like sound waves. So if you're sat at the bottom of a pool holding your breath, because why wouldn't you? You can still hear sound from above, right? That sound is coming down through the water, it's moving down. If someone sticks their hand in the top of a swimming pool when you're at the bottom and waggles their hand backwards and forwards, you're not going to feel movement associated with that. Okay? So those are the different types of waves, and that's why some will travel through the Earth and some won't. And those P waves, the ones that arrive first, travel the fastest. Makes sense. They travel at about 13,000 miles per hour. And those S waves travel probably only about half as fast, maybe 7,000 miles per hour. Okay? And then we have our surface waves, which are even slower because they have to come around the surface as well. And there's two types. There's love waves and rally waves. I don't want you to worry about those names. But you can see, again, there's different senses of motion associated with those. Love waves are backwards and forwards, and rally waves are sort of circular. And these are the damaging waves. Okay. So these seismic waves can actually tell us a lot of information. There are three things that we can learn from seismic waves. First of all, the location of the epicenter. So we can use the arrival times of these waves to work back and think about how far away we are, and therefore where the center of the earthquake must have been. We can get at earthquake strength from these waves and our record of them. And we also get information about the Earth's interior. So first of all, I want you to look at our little seismic trace at the top. And you can see that the P waves arrive at a certain point, and then the S waves arrive. And the problem you have, if you're just at some seismic station, you go, earthquake, and you look at your seismograph and you see the P waves and then the S waves, is that you don't necessarily know when they started. Because you'll know, because you all drive a car, that you can use the distance and the time and things to get at speed. And we know the speed of these waves, and we know how we have a sense of the time. We want to know the distance. Okay? But we don't know the exact time when the earthquake occurred. So we can't directly use that idea. What we instead have to use is the difference between the P wave arrivals and the S wave arrivals. Because we know how quickly both of those travel. So if we know the time difference between those, we can get back to distance. So, and this is what my graph shows here. You can see that the lower line shows P waves, showing distance in kilometers from the focus along the x-axis versus time. So in our example here, at 4,000 kilometers distance from the epicenter or the focus, then it takes our P waves 7.4 minutes to arrive. And it takes our S waves, the upper line there, 13.7 minutes to arrive. Okay? What we can't measure, we don't know the 7.4 minutes or the 13.7 because we don't know when the starting point was. But what we can measure is the difference between those. So we know that there's a difference between those values of maybe, 6.3 minutes. So we can look at the time difference between those two lines, and where it lines up with 6.3 minutes, we know that that is the distance that from the focus or the epicenter. And I'm going to give you a chance to do this now. So hopefully you followed that. So if the time difference between the P waves arriving and the S waves arriving is 10 minutes, how far away is the epicenter of that earthquake? So talk to your neighbors for a couple of minutes, see if you can work out roughly where it is, and then I'll open up the vote. Okay, so I'll start the vote. If you have an idea already, vote, but I'll give you a couple of minutes if you still want time to think. The TAs are scattered around, you can ask them as well. Okay, I think we've got most votes, so if you haven't had a chance to put your answer, give you a couple more seconds. Okay, so let's see if we have an idea or if everyone's completely and utterly lost. Ooh, 50%. I think that's the best I've ever got on this question. Good work. Okay, so C is the right answer, and I'm going to tell you why. So remember, I mean, it's actually a difficult graph to read. I do understand that. Okay, so the time we have is the difference between the P waves and the S waves. So if we look, we want this difference between these two lines to be about 10 minutes. So if we look at maybe 5 kilometers, then the P waves arrive maybe at 8 minutes, and the S waves arrive maybe at 16 minutes. We've only got an 8-minute difference. So that's obviously too close. If we look at 12 kilometers, our P waves maybe arrive at 15, our S waves maybe arrive at 28. We've got too much of a time difference. There's like 13 minutes there. If we look at 8 kilometers, our P waves arrive at maybe sort of 10, 11. Our S waves arrive at maybe 20, 21. So there's a 10-minute difference. And then we can look at that, wherever that distance is, and we can look down and say it must be 8 kilometers away. Okay? And we'll have a chance to practice this in discussion next week, which hopefully won't be delayed by rain, which isn't very helpful. So, thinking back, does anyone know the answer to this? So we have our one record, so we know from our one station, from our seismograph, how far away we are from the earthquake. Does that tell us anything about where the epicenter actually is? Because where could that epicenter theoretically be? Anywhere on that big circle, right? It could be anywhere on that circle. So how many more seismographs do we need to pin it down to one place? 2. 2 from the back there, absolutely. Because if we have another seismograph, then we still have 2 possible locations. We look at where those lines cross, but there's still 2 possible places that it could be. So we need our third little seismograph, and then this, where all of those 3 circles intersect, that's going to be our epicenter. And this is called triangulation. And the clue is in the name. There's 3, so it's triangulation. And this is something that is going to be my challenge for you in discussions next week. I'm going to hide a dime on the main lawn, and I'm going to give you some seismographs, and you're going to work out where that dime is by triangulating. Okay, so it should be a lot of fun, and it shouldn't be as wet as this week was. Okay. So the second thing that we can learn from our seismic waves is the size of the earthquake itself. And this isn't a shock to anyone, because you know that the bigger the earthquake, the more shaking or the more violent the shaking you feel. Okay? So what we can do is we can look at, say, a set distance away from the epicenter, and we can look at how much amplitude, so the height of those waves, okay, on that record, the amplitude of those seismic waves. And if we look at the amplitude, then this is where our log scale comes in, okay? Because what we're saying is that a magnitude 7 earthquake is 10 times bigger than a magnitude 6. And a magnitude 6 is 10 times bigger than a magnitude 5. And so our magnitude 7 is 100 times bigger than our magnitude 5. It goes up by 10 each time, a factor of 10. If we actually look at the energy put out by that earthquake, then it actually goes up by 30 each time. So our magnitude 7 earthquake gives out 30 times more energy than our magnitude 6, which gives out 30 times more energy than our magnitude 5. So a magnitude 7 earthquake is actually 900 times more energetic, more energy is released than a magnitude 5. So you can see it scales really quickly. So if you think about a magnitude 9 earthquake, that's giving 30 times 30 times 30 times 30 times more energy than our magnitude 5. And that's why those are so substantial, and why when we start getting into the 9s, things like the huge Chile one, the huge Alaskan one, the Sumatran earthquake, the Japanese earthquake was a 9. We've had a whole bunch very recently. It actually even affects the length of day by ever so slightly. That huge Sumatran earthquake actually slowed down our spin as the Earth ever so slightly, just by a fraction. But they're substantial, they're huge, okay? And then lastly, we have Earth's interior. And we talked about this briefly further back, because we said that we know that the outer core is liquid. Well, how do we know? We know because of that difference between the P waves, the compressional waves, and the S waves, the shear waves or the shape waves. Because those P waves, just like sort of sound waves traveling through water, will go through liquid. They'll go right through the middle there. But S waves will stop when they get to that inner core. They won't travel through the inner core. And so what happens is that on the other side of the Earth, we get P waves traveling straight through, but we don't get any S waves associated with them. And so if we look back at sort of reconstructing the geometry of those, we can work out whereabouts that change between solid and liquid happens within the Earth. The other thing that we can learn from them is that those seismic waves actually travel at different speeds depending on the density of the rock they're going through. And that means that they have these funny curved paths because they actually end up refracting whenever the density changes significantly. And refracting, remember, is that change of angle associated with a change of density. So by having a network of seismic stations all over the Earth, we've been able to get a much better sense of what the interior of the Earth looks like and what it might be made of even. Okay, so let's think about earthquake damage, because this is something that's going to affect us. We have two different types of earthquake damage. We have primary, which is just those waves, that ground motion, that shaking backwards and forwards associated with that seismic energy coming out, but also a horizontal splitting, that offset that we saw in the fence associated with movement along the fault. So those are our primary sort of mechanisms for how earthquakes can damage buildings and structures. But we also have the secondary effects, and we've already talked about a couple today, which is that we have fires. And fires were really important in that 1906 earthquake. They caused a huge amount of damage. And remember, it's because we may start fires because gas lines break and there with sparks and power lines down and things like that. But of course, at the same time those break, we also break our water lines. And so it's going to be very difficult for firefighters at that time, first of all, to travel through the city, but also to fight the fires. And so there will be probably entire neighborhoods that get sort of swallowed by fire, unfortunately, and it's very sad. Things like landslides. In LA, this is hugely important. In that Northridge earthquake in 1994, we had something like 11,000 landslides. So all those beautiful, expensive houses on the top of cliffs, you know, they're really not that good an investment. I wouldn't buy one, as beautiful as they are, not that I could afford it. And then we have things like liquefaction. Has anyone ever seen liquefaction in action? Has anyone ever stood near, just on the sand, near where the water's been coming in and out, and then jumped up and down or tapped their foot? And it goes sort of liquidy, it's like quicksand, and you sink a little bit. Okay, next time you're at the beach, do this, because that's what liquefaction is. You have lots of water between individual sort of soil and sand grains and things like that. And what happens is that when they're all shaken around, some of that water gets squeezed out. And it gets squeezed out, and the whole sort of sediment starts moving like it's a liquid. And obviously that's not good if you have your nice house built on top of it. It tends to lean a bit and sink. Okay? And then, of course, we have tsunamis. And this is what we've really been seeing in the last decade and hadn't seen for quite a while before then. And they're nothing to do with tidal waves. Don't call them tidal waves, I'll get cross. They're tsunamis, and they're due to that movement of the seabed. Okay, they're associated with things like landslides, volcanic eruptions can also sort of cause them, but it's where the seabed moves up or down by a significant amount, and that moves the entire water column above, and then that sort of races out very, very quickly at the same sort of speeds as airliners. And they can be huge. So I think, is this my next example? No. My example of tsunami is in the Japanese earthquake in two years ago. Some of the waves reached 40 meters. That's really huge. That's sort of twice this easily, if not 3 times this. Okay? So not fun things. So if an earthquake was to happen right now, what would you do? Run outside as quickly as possible, post it to Twitter, try and get to a doorway, or get down on the floor. See how many of the class we still have at the end of this. Okay, shh. Time to, got 5 more minutes and I've got important things to show you. Okay, so we still have 49% of the class at least, okay. So yes, absolutely. A lot of people think, and because it's what we used to be told, that you find a doorway to shelter under, and that's all very well, but it only works if the doorway is actually a structural support in some way, and most doorways these days aren't. They don't have big sort of girders running along the top. So the safest thing to do is to get in front of your seat and protect your head. If you're in bed, what should you do during an earthquake? Stay in bed. Okay, more people in the Northridge earthquake injured themselves trying to sort of walk across broken glass in the dark than they did just by actually things falling on them. Okay, so most destructive earthquakes, you can see that these things can kill hundreds of thousands. But the number of casualties that you get associated with earthquakes varies partly because of the size of the earthquake, but that's not always the biggest predictor. Things like building codes. How populated the area is. In Alaska, we get gigantic earthquakes, but there's so few people up there that it doesn't make as much of an impact. Whereas things like in the Haiti earthquake, there are a huge number of people and not great building codes, and so a lot of people were very hurt in that. And things like in Sumatra, most of the deaths there didn't occur from things collapsing. It was the tsunami, again, that killed people. Things like education will help. There's a whole variety of extra features that are due to just us and how we behave as humans that will have things to do with how many people are hurt. And we use this scale, this Mercalli scale, to look at. So we have the Richter scale, which tells you the amplitude of the waves, but really probably what you want to know is how much damage there will be. And so this is our scale, and it goes from basically 2 to 3 to 4 in the paler green, which is like you barely feel it, probably if you were walking you didn't, up to things like 10 plus, where you more or less have to tear down structures if they survive because there's so much damage. And why am I showing this? So this is the rough idea, and then you've got descriptions there, which I won't go through, but hopefully you'll be interested enough to read this. And this is what happened in Japan in that 2011 earthquake. And there was actually 5 minutes of shaking. That's from like now to the end of class. That's crazy. And it caused sort of $14.5 to $36 billion of damage. And of course, a lot of the deaths that occurred were unfortunately due to that huge tsunami, rather than the buildings themselves. And the Facebook post I had on the class website yesterday shows those skyscrapers swaying backwards and forwards. There's amazing engineering that we can do now to help prevent deaths. So why am I showing you this? Because we are in that nice red area. We can't predict when an earthquake will happen exactly, but we can say sort of in likelihood that some areas are much more likely than others to have earthquakes based on things like that recurrence time. And we are in that nice red area, okay? I've told you there will be an earthquake. So this is the Loma Prieta earthquake. This was 6.9 up in San Francisco. It was about 15 seconds of shaking and 63 billion deaths, $6 billion US. And remember that because this is what could happen here. This is our best sort of guess at what a reasonable estimate for the next earthquake would be that would happen on the San Andreas Fault. It would start in that Salton Sea area and then move along the fault towards the north. And in particular, look at those colors. we're not going to have a very fun time of this. We won't have as long as shaking as in the Japanese earthquake, but we will have really intense shaking, especially along the fault. But also you can see in the LA basin itself, there's very, very strong shaking, and that's to do with the type of material that the city is built on. Around the edges, maybe where we are as well, we're pretty much on bedrock. We're solid rock. In the LA basin, it's a basin. It's been collecting sediment, and that sediment will move and it will amplify the waves coming through, and so you'll get much stronger shaking there. Okay? And this is the idea. It's probably around 2,000 deaths, 50,000 injuries or so, $200 billion in damage. And I've got a bunch of things there. So there you can see in real time how the earthquake waves move through. Oi, not quite yet. But the third thing I wanted to show you is, unfortunately, our scenario, you can't read it immediately because the government webpage is down, but I have a copy of it, and I'll show you. Okay, 2 more minutes. And I want you to read that quite carefully because it's like a little sort of Hollywood film. It says, 2 minutes before the earthquake, what happens? 30 seconds after the earthquake, 2 days after the earthquake, 3 months after the earthquake. And the really big question is, we're going to have to boil water for weeks, if not longer, in parts of LA, maybe up to a year. People aren't going to sit around and do that necessarily. They'll be moving away. Will they stay away? Will they come back? And lastly, extra credit. Silence all of a sudden. How many people in the room actually have an earthquake preparedness kit? 1, 2. Okay, not enough. I care deeply about you all, and I want you to survive an earthquake. And so there's a little information there which is actually functioning, even though the government isn't. So prepare yourself an earthquake kit. Send me a photo and a list, and you'll get your 5 extra credit points. Okay, thanks.